Hello and welcome to an exciting global edition of Astronomy News with the Cosmic Companion. This week we examine a stunning glitter seen around a supermassive black hole. We also journey to Mars, where the Mars Express orbiter finds 3 more salty lakes beneath the surface of that world. The red planet is also an easy find in the sky this week, and we're going to take a look at how to find it. We'll also journey back in time, where and when we'll see 6 galaxies huddling around an ancient quasar and learn how the largest structures in the universe were born. The black hole at the center of the galaxy M87 was at the center of stories in 2019, as astronomers recorded a detailed image of the region surrounding one of these strange bodies for the first time. Now, new analysis of older data from that black hole recorded by the Earth Horizon Telescope Network reveal the ring around that supermassive black hole is glittering. Researchers determine this ellipse of electromagnetic energy surrounding the black hole at the center of M87 changes brightness and moves over the course of several years, while the size remains the same. Next week on this show, we'll be joined by Dr. Maciek Bielkis, astronomer at Harvard University, who led this discovery. Be sure to tune in then. The Mars Express orbiter recently found 3 previously unknown lakes of water beneath the surface of Mars. These join another larger lake first seen in 2018. The largest of these subsurface bodies of water is about 30 kilometers or 24 miles in length. In order to remain liquid, these lakes would have to be extremely salty, and that could potentially hinder any Martian life which developed in that ecosystem. However, the presence of liquid water on Mars is an exciting find in the search for extraterrestrial life. Speaking of Mars, the red planet is making a close approach to Earth this week, and it will be the closest the two worlds will be for the next 15 years. The red planet is seen shining bright in the eastern sky during the evening, easily visible to stargazers. Seen as a bright red dot, Mars is currently brighter than the massive planet Jupiter or any star in the sky. Today, October 6th, Mars and Earth are the closest they will be until the year 2035, so enjoy the view.
Looking deep into the universe, we see backwards in time, and the oldest light in the universe holds secrets to how everything around us will, one day, end. Meanwhile, stars, planets, and galaxies dance in an intricate ballet, occasionally giving birth to life. We are a fledgling species, just beginning to visit other worlds. We are a way for the universe to understand itself. The Cosmic Companion strives to bring the universe down to Earth, and we depend on your help to make it happen. For information on subscriptions and ways to donate to this program, please visit thecosmiccompanion.net. Thank you.
Astronomers at the Very Large Telescope have found 6 galaxies orbiting an ancient quasar, fueled by a supermassive black hole containing the mass of 1 billion suns. These bodies are seen as they appeared when the universe was just 900 million years old, roughly 7% of its current age. This finding suggests that the largest black holes in the ancient universe may have been fed by behemoth tendrils of gas, which later grew into the cosmic web, the largest structures in the cosmos. Join us on the show October 20th, when we'll talk to Dr. Roberto Gilli of the National Institute for Astrophysics, leader on this study, who will join us from Italy. This is a very special global episode on Astronomy News, the Cosmic Companion, as we talk with Dr. Amanda Karakas of Monash University, speaking from Melbourne, Australia, as well as Dr. Chiaki Kobayashi from the University of Hertfordshire, joining us from London. These researchers are at the heart of the new study showing how much of the gold in the universe was produced by a particular type of supernova explosion. This week on Astronomy News, the Cosmic Companion, we're happy to be joined by two special guests in a global episode. Amanda Karakas is an astrophysicist at Monash University, and she is joining us from Melbourne, Australia. And Dr. Chiaki Kobayashi is an astrophysicist at the University of Hertfordshire. And she's kind enough to be talking to us from London. Welcome to the show, both of you.
Thank you.
Thank you.
All right, so let's start with you, Dr. Karakas. Can you give us a brief description of how nucleosynthesis and how materials are formed in the cosmos?
Yeah, so at the very beginning, we had the Big Bang, and that formed hydrogen and helium essentially under conditions of very high temperatures and densities. But that's really all that was formed at that stage. And then we had a process of star formation and galaxy formation, which Chiaki will tell you more about. But then once we have stars start forging elements deep inside their interiors, and all the elements heavier than essentially lithium were formed deep inside a star. So they are essentially giant pressure cookers, if you like, that fuse together light elements into heavier elements through thermonuclear reactions. And the various types of stars will fuse different sorts of elements depending on their mass and how hot they get. And this is something that we've been following in detail, and in particular looking at not just the elements lighter than iron, but also how we make elements heavier than iron, because they have to be made through different sorts of nuclear reactions, still nuclear reactions under high temperature conditions. They're made through different sorts of reactions inside stellar interiors, inside stars of different types. And so essentially that's really where cosmic element synthesis happens, inside a star somewhere.
It's wonderful. And can you expand on that a little bit, Chiaki?
Yeah, so the Big Bang can make only elements up to helium. That's only number 2. In a periodic table, you see a long list of elements. Big Bang can do only number 2. And all the rest should be made in stars. And but we vaguely know they should be in stars. We don't know exactly what kind of stars are actually making the rest of the elements. And that's what we do in this paper.
That's super. And the a lot of attention was paid to the production of gold. What makes gold so interesting?
Well, first of all, we want to make more gold. That's a non-scientific interest as well. But also in scientifically, it's actually very difficult to make gold. There was a prediction that gold is more massive, more heavier in our context than iron. Iron is possible to be made at the end of the very massive stars, let's say, more massive, 10 times more massive than our star, our sun. But even though only iron is formed at the very end of their life, Gold is much more heavier. We need a very, very special environment to form gold. There is some theory that are in a very special environment. For example, if the two very dense core formed by neutrons crush to each other, it may be possible to form gold. There was a theory for that. We included that. We included that effect, but still not enough. We can't make enough gold. That's what we found this time. We really wanted to make more gold, but we put all possible solution to make gold, but still not enough.
And Amanda, so as Carl Sagan was so fond of saying, we're all made of star stuff. And, and the same goes for heavy elements are all formed in stars either through reactions or through supernova explosions. But why are they not making enough gold to account for what we see out there?
Yeah, it is that Carl Sagan statement. It's a cliche, but it's a true one. I do often sometimes start my public talks with that, pointing out it's a cute statement, but it's true. We are essentially made of star stuff, except for the hydrogen and helium, as Chiaki said. So gold is problematic because so there are a number of different. I guess one of the things that came out of our study, and this is something we've known this for some time, but we really showed it here, that all elements have more than one type of star will make more than one element. So we take an element like gold, it has a contribution from these merging neutron stars that Chiaki mentioned. So these are the cores of these burnt out massive stars. It's also made in the explosions in massive stars, but a little bit's also made in dying low mass stars. So it's made from a number of different sources. And when we added up the contribution from all of these sources, we found there just wasn't enough of it. So why is that? That's a good question. We think it's probably because we can account for the production of other elements in enough quantities. We think the issue with gold might come down to some of the nuclear physics. So the probabilities under which these reactions happen. Because especially if you're making heavy elements heavier than iron, it depends on, I don't know how technical you want me to get, but it depends on essentially the thermonuclear rates of how probable it is that various isotopes can capture neutrons. And this probability depends on not a particular element, but on a particular isotope. So the number of neutrons and protons, etc., in that individual isotope. And each isotope out there has its own particular probability, how much it likes to capture neutrons. And especially when we talk about the conditions inside merging neutron stars and massive core collapse supernovae, we're dealing with such high numbers of neutrons that we end up making really radioactive isotopes, really heavily radioactive isotopes, and we don't know what their neutron capture rates are. So we don't know the probability of. So the nuclear physics, I suppose, is unknown, and this is where we think possibly the main uncertainty lies in some of these calculations. There are other sources, of course, but that's one thing we can pinpoint to.
Wow, that's really interesting. And Chiaki, of course, stars are not solitary. They most live within galaxies, including the ones most familiar to us. Can you tell us a little bit about how stars interact with other stars within the galaxy and how this affects the production of heavy elements?
Yeah, so stars are made of many millions of stars. Most of them are actually, we call it low mass stars, like our sun. They produce a bit of elements, hydrogen, helium, a bit of heavy elements, but not so much gold. We have to have first of all, very massive stars. Let's say 10 times more massive than the sun. That's a necessary condition first. They explode as supernovae and form a neutron star. When they explode, maybe possible to form a very heavy element like gold if they are in a very special state, like rapidly rotating with magnetic field with a jet explosion. That's one way to form gold. If they don't, they become neutron star. Neutron, in the universe, it's made of equally of proton and neutrons. Usually it's equalized. But in a neutron star, as you can imagine from the name, it's made of neutrons. It's not made of protons. It's made of neutrons. Very special case. In that case, neutron star is already a special case, and if we merge two of them, something else could happen. That's another special occasion. So, already we are talking about very, very special case out of a very special cases to form very heavy elements. And in a galaxy, most of stars are like our sun. It's not so exotic, I would say. It's still useful to produce carbon, oxygen. That's very important to form our body. But to make gold, we have to have something beyond. Very rarely, those massive stars are formed in the galaxy, in a long history, accumulated it, and we now have a bit of gold on the Earth.
And so, Amanda, in your paper, you had some talk of what are called magneto-rotational supernovae and quasar supernovae. For those who may have seen those terms for the first time, can you give us a brief rundown of what those are and what role they play in this study?
Yeah, Chiaki actually hinted at that before.
Yeah.
She didn't use the names, but she essentially explained what they are. So they are unusual massive stars that are either spinning more rapidly than some of their cousins, maybe. And because of this rapid rotation, they also have very strong magnetic fields. So when they explode in an unusual way. They release these jets that come out of the stars, and that gives us conditions that are more favorable for making heavy elements. These elements heavier than iron, than a regular core collapse supernova, essentially. So they're essentially just really rapidly rotating energetic supernovae that also have these jets associated with their supernova explosion, and they give us conditions that are just more favorable in the supernova explosion, in the ejection itself, for this production of heavy elements.
And so this is a free for all. What other elements seem out of whack out there? Which other ones might make for some interesting studies do we need to know more about?
Well, one thing we didn't study at this stage, and I know Chiaki and Maria and I have talked about this, is looking at the isotopic ratios of some of these elements. Because in this study we added up. So even though when I do my calculations and when Chiaki does her calculations, we do follow the individual isotopes, but in the end, she just added it up to give the elemental contribution as a function of time. But we're also interested in the isotopic ratios, because many of these heavy elements have many isotopes. And so we're interested in also following, and we can compare this to for example, the ratio of strontium 87 to 88 measured in the solar system, for example. There are some observations, not many, but at least there are some observations we can use. So we really want to follow the isotopic, because the isotopic composition really pinpoints the nuclear physics. And this is, if we want to understand the nuclear physics background, we need to follow the isotopes. And so for example, the gold problem might be alleviated through looking at the isotopic ratios.
That's interesting. And what future tools are either of you looking forward to having at your disposal in the coming years?
I'll let Chiaki answer that one.
Yeah, so this past analysis, we showed that from looking at galaxy in the past, we can see how much elements should be from what kind of stars. That's the first step we did in our paper to now. But if we look at the past of our galaxy in more details, we can dig out more information. We want to see more observational data from the past. Fortunately, if we find all the stars that are much older than our sun, let's say they are formed just after the Big Bang, after the formation of the universe, they still survive, containing the information when they were formed. We can look at them and analyze the abundance. How much gold should be there at the time. We know how much gold should exist now from the sun, but we wanted to know more, how much should be there in the past. So that's the extra information we can connect our current theory to the prediction theory in the past. It's very difficult observation.
Wow, that's fascinating. Well, thank you both so much for being on the show. It was wonderful to have each of you here.
Thanks for asking us to be here.
Thanks.
You're welcome. And that was Dr. Amanda Karakas at Monash University and Dr. Chiaki Kobayashi of the University of Hertfordshire. Next week on Astronomy News with the Cosmic Companion, Dr. Maciek Bielkis, astronomer at Harvard University, will be joining us from Gdansk, Poland, discussing his work revealing glittering around the supermassive black hole at the center of the M87 galaxy. Watch or listen to this fun, exciting episode starting October 13th. And join us each week on Astronomy News with the Cosmic Companion as we bring space and astronomy news and education together with groundbreaking scientists directly to listeners and viewers around the globe. We depend on support from viewers like you to help support this program with a one-time donation or a paid subscription starting at just 99 cents a month. Please visit thecosmiccompanion.net/support. Please stay safe, stay healthy, and keep your wonder alive. If you live in the United States, you have not done so, please remember to vote. If you enjoyed this episode of Astronomy News with the Cosmic Companion, please download and share the episode on YouTube, Facebook video, or on any major podcast provider. For more details on space and astronomy news, please visit thecosmiccompanion.com or thecosmiccompanion.net.